Now let's do some problems that require the knowledge of trigonometry. So we're gonna do trigonometric integrals. So I'm gonna call number 2 trigonometric integrals. Trigonometric integrals. So we're gonna divide this into several different cases. So we're gonna go with I'm gonna call A. So integrals like this. So let's say we have sine some power x and then cosine some power x dx. So how we do a problem like that? We're gonna look at whether m or n is odd. So if the method is this: if m or n is odd, we're gonna use u equal the other one. So if one is odd, pick the other one. So that's how we do it. So it's the other one. So we use the other one. So let's see how this trick gonna work. So you can see it's very simple. So as an example, we can try this problem. So let's say sine 3x cosine 6x dx. A problem like that. So you can see here uh, m is odd, so that means we're gonna pick the other one. So that means you're gonna pick u equal the other one, that means the cosine one, not the cosine 6 but just the cosine. And then I take the derivative. Once you take the derivative, you can see derivative of cosine is negative sine x. So that means we're gonna pull one sine term for the derivative part. Okay, we're gonna pull one sine term because you can see there's a sine here. So we're gonna pick one. That's why it has to be odd. So we can pull one. So we're gonna pull one of them. So that means we can rewrite this integral like this. So you can see that you can write this one as sine. We're gonna pull one, so we have only x 2, and the cosine 6, no problem here. And then we leave that sine term here because that's the one we pull for the derivative part. So we can leave it. We are not going to touch that because you can see this is simply the negative du. This is simply negative du, negative sign coming from the derivative because there's a negative sign. Okay, now what we can do, we can rewrite the rest of the integral using cosine, everything else using cosine. I'm going to put like a box there. That's the substitution part. So we can write the rest of the integral using cosine. That means sine squared you can write as 1 minus cosine squared x. Cosine 6 we leave. And what we can do, we can rearrange this one. If you want, you can put negative sine x dx. But remember, this is a product, so we put a bracket here and put a negative sign in front just to match. So two negative signs. Now we can substitute. Okay, so negative. We can solve for cosine. Cosine is simply u. So 1 minus u squared u to the 6. And everything else, this whole thing is simply du now. So that means this is du. Okay, good. How to do this? Distribute. So if you distribute, you're going to get negative. The integral u to the 6 minus u to the 8 du. This is very easy to integrate. So this is negative u to the 7 over 7 plus u to the 9 over 9 plus c. But u equal cosine, you put that back in. So this is cosine 9x over 9 minus cosine 6x over 7 plus c. So that's what you get. Okay, very simple. So let's do another problem. You can see that this same trick even works for other cases as well if there's an odd power. See, other function pretty much can be anything actually, because only thing is the odd power. If it is in the numerator, the other term can be even in the denominator, square root, any other thing. So for example, it works for this problem as well. So for example, works uh, for some other cases as well. Some other cases. Some other cases as well. So you can use the same trick even to integrate a problem like this. So let's say cosine let's say you have cosine x square root and then some other power. So let's say sine 5x dx. So you can see that there's an odd power. So that means you're going to pick the other one as a substitution. So that means you're going to pick u equal cosine x and the same argument. So du equal negative sine x dx. So that means what you're going to do as before, we can write cosine x and then this one you can write as sine 4 and then we're going to pull one sine for the derivative part. That's why it has to be odd. And you can see this one you can also write as using a cosine. So everything else you can write using cosine. So you can see this is simply you can write this on a sine squared squared. Sine squared means 1 minus cosine squared x using the Pythagorean identity and you square it. Now what you're going to do, you can substitute for cosine. So and then this is simply the derivative part. So this is simply negative du and you can see that you can finish the problem now. Okay, so I'll let you finish it, but you see the argument is very clear. So you can substitute for that. We can write as sine squared. Sine squared is 1 minus cosine squared, but you can write sine 4x. You can write as sine squared squared. So then you can do that. Okay, so that's about that. So let's try to go to the other type. So what's the other type? So you can see that we assume that one of the powers is odd. What if both powers are even? So we're gonna same problem sine mx cosine nx dx, but in this case we can assume that both m and n are even. Okay, so we can assume that both even. So if both even, what we can do, we can use half angle formula. Okay, so use a half angle formula, half angle formula. Actually, you get the half angle formula using the double angle formulas. Okay, so what are the formulas? So we're gonna use these. So we know that the sine square theta equal 1 minus cosine 2 theta over 2. So you can see this is the half of. So you see that 2. So you're gonna get the half of 2 theta. That's why we call half angle. And then also we have for cosine the same thing with the plus sign, 1 plus cosine 2 theta over 2. So those are the two formulas, one with plus sign, one with minus sign, both cosine. That's the interesting part. You can get these formulas using the double angle formula. Okay, derivation is very simple. Okay, good. So that's the kind of idea. What we can do is we can try a problem or two, just one problem. How about this one? Let's do like a simple one. So the example. So let's say we can integrate 1 plus cosine 2 theta. Let's say not 2 theta, like let's say 4 theta. 4 theta square root, something like that. So if you see something like that, I mean, it's obvious that you have to use some kind of trigonometric identity. So we can use the double angle, this half angle formula here. So that means you can see inside, you can see the 1 plus, so that means the cosine one. So that means you can first rewrite this one. We assume that these are all positive, so that's the assumption. You can write this one as twice cosine, get the half of the angles of 4 theta become 2 theta. So it's square 2 theta. Okay, and the square root with under square root. So you can write it like that. That's the first step. You use the half angle formula here. You get half of that. So that's a half of this angle. Okay. So you get 2 theta but squared. 2 coming from because in the denominator, so that you have to multiply by 2. And then you can simplify. We assume these are all positive. So using that assumption, you can write this one as square root 2. You can pull it out. You can write this one as cosine 2 theta d theta. The assumption is we assume that these are positive. Now we can just integrate this as a cosine. So that means this is a sine. So what you need to do is you just divide by 2. So that means you're gonna get square root 2. Integral simply become 1/2 sine 2 theta plus c. So you get that uh, which is equals to 1 over um, square root 2 sine 2 theta plus c. Okay, so you can see it's not that difficult, but we have to use the half angle formula to get the answer. So let's try to move on to the next type. So which is I'm going to call C. So what we have is we're going to see some tan powers and secant powers x dx. So a problem like that. So what's going to happen? So the idea is this. So if we have so if n is even, if n is even, then we're going to pick u equal tan x. The reason is if you look at the derivative of this one, it's going to be secant squared x. So we're going to pull out secant squared term and try to rewrite everything else using tangent, because we know that there's a formula. So for example, we know that the secant squared x is equals to 1 plus tan squared x. So you can rewrite everything else using tangent, using this identity. So so what we did was we picked u equal tan x, and then similarly, if we have let's say if n is odd, if n is odd, n means the powers of secant is odd, then you're going to pick u equals secant x. So this it's not 100% guaranteed that it's going to work, but it's going to work most of the time. So let's say du equal, if you take the derivative, which is secant x tan x dx, and again now what we do, we try to write everything using secant, because we know that the squared x tan squared x is equals to uh, secant squared x minus 1. So we can use that identity to rewrite everything using secant. So now what we do, we use that. So you can see that in the first case, so it doesn't really matter what the powers of what m is. M can be any fractions, negative, square root, things like that. So let's look at a problem just to see um, how we can use the idea. So again, so if n is even, we can use u equal tan x. If n is odd, we can use u equal secant x, and this works most of the time. So as an example, let's look at this problem. So let's say we have tan, let's say square root. Actually, we did this problem in the lecture. So we can see we did a very similar problem in the lecture. Secant, so let's say we'll use what same variable. Let's say theta. So secant theta d theta. So let's say this is a problem, and you can see this is we have 4, so which is even. So that means we're gonna pick u equal tan theta, and you can see du equal secant square theta d theta. That's the derivative. That means we're gonna pull secant squared term out of the integral for the derivative part. So we can rewrite this one as tan the half power to the square root, and we're gonna pull one secant term out. So secant square theta, and we also we have secant theta square theta d theta. So this is the derivative part, we leave it like that, and everything else we can write in terms of tangent. So which is tan half theta. So this is 1 plus tan square theta. So this is secant square theta d theta. That's what you get. Now we're gonna plug in for tangent theta. So you can see this is u1 half. This is 1 plus u squared, and this is du, because you can see this is simply du part. Okay, so du. Okay, now we can distribute and integrate. So if you distribute, you're gonna get u1 half plus u5 half du. So this is very easy to integrate. So you get 2/3 u3 halves plus 7 2/7 and u7 half plus c. Now you put u back in. So this is 2/3 tan 3/2 theta plus 2/7 tan 7/2 theta plus c. So that's what you get for that problem. You can see it works very well. Only thing we worry about, secant should have an even power. We write everything else using tangent. So that's excel. See, you write everything else using tangent, and then you can substitute for that. So that's the kind of idea. So it works for like a large class of problems. So you can try this as a practice problem. So why don't you try this one? So you can try, let's say you have secant 4x, I mean any even power, just put even power, and then let's say we have tan theta square root d theta. Okay, so you can see yeah, this problem works very well. This argument works very well because secant has an even power. Now let's see what if secant has an odd power. So let's try this problem. So let's say we have tan 3 theta. Let's yeah, we need to get used to some other variables as well. So let's say x. So tan 3x secant x dx. Now you can see secant has an odd power. So if there's odd power, what we're gonna do? We're gonna use the secant substitution. So you're gonna pick u equal secant x, and then we're gonna see, we should have the derivative. You're gonna see that the derivative is secant x tan x dx. So the goal is to see whether we can pull out secant x tan x. Okay, so if we can do that, then we can use this argument. So we can actually do this here. So we're gonna leave tan squared x, and we're gonna pull one tan term for the derivative. Now what we're gonna do is we're gonna rewrite everything else using secant. So we can do that because this is simply secant squared x minus 1, and this is secant x tan x, or you can simply write a du, but I like to have same variable in one equation. So this is du. Okay, now let's replace everything. So you can see this one you can write as secant squared. Secant squared means secant means u, so this is u squared minus 1 du. Now you can see that you can integrate term by term. u3 over 3 minus u plus c. So let's put u back in. U means secant theta. So that means this is secant cube x over 3 minus secant x plus c. So that's the answer. So you can see it works very well. The substitution was u equal secant x because secant has a even power, and c with the and secant has even power. So that's the kind of idea here. Good. So let's try to do another problem just to see what else we can do. So how about this problem? Let's say we have tan 4 theta d theta. So here secant has an even power. Power is 0. So that means so we can do a trick like this. So what we can do, we're gonna pull one tan term, and then we have tan squared. So like that. And then what we're gonna do, we're gonna rewrite one of the tan using secant. So you can say secant squared theta minus 1 d theta, and we can distribute that. Once you distribute, you're gonna see that you're gonna get tan squared theta secant squared theta d theta minus tan squared theta d theta. First integral is very easy to do because you can see that this is the derivative of the first term. So you can use the 4 formula trick because this is just a power rule. So that means you can simply create tan theta as x. So that means it's going to be 1/3 squared. So in this case tan, so tan 3 theta. So that's it. That's the first integral. It is the 4 formula trick for the first one. So for the first one, we use the 4 formula trick, or just use substitution. U equal tan theta, but you can skip that when the complete derivative is there. And then next one, we can use the same trick. We can rewrite this one as secant squared theta minus 1, and then we can integrate term by term. So it is 1/3 tan cube theta The first one gonna give you tan theta. Next one negative positive, so you get theta plus c. So that's the final answer for that problem. And then we can do another trick. So sometimes you can use the integration by parts for certain problems. So let's try to do a problem using integration by parts. How about this one? So let's say you have t secant t tan t dt. We did the same problem in the integration by parts problem also, but I want to tell you, like, because it's important. Now the goal is, that when you do integration by parts, you have to pick u and dv properly. So what we can do, because we know that this part is very easy to integrate, so we're gonna pick this one as dv. And the next is, so this is u, because we find u which is easy to take the derivative. We define dv, which is easy to integrate. So you can see both works very well. So u equal t, dv equal secant t tan t dt. So take the derivative, which is du equal dt. Take the integral, which is simply the secant t, because we know that the derivative of secant is secant tan. Okay, so we have everything we need, uv minus v du. So if you plug in here, you're gonna get uv, which is t secant t minus v du, that means secant t dt. So what you get is t secant t. We know the integral of secant t, which is natural log. That's something you didn't remember. Natural log secant t plus tan t, which is the integral of secant t. So that's the final answer. T secant t minus ln secant t plus tan t. Okay, so that's it. So I'm gonna give you some like 3 other formula that you want to remember. So these are the formulas. So we have integral of tan t. Let's go with x. So tan x dx, which is the natural log secant x. So we prove this one, plus c, and then we have cotangent tx dx, which is natural log sine, plus c, and then we have secant x dx, which is natural log secant x plus tangent x plus c, and then the cosecant, which has two versions. One is the negative sign inside, like that, and one has the negative sign outside, like that. Okay, so those are the formulas that you want to remember. Okay, so there are 2 formulas for secant. Anything works. And then as the last part, we are not going to do a problem, but I'm going to recall what we did. So we have like product like that, sine mx cosine nx dx, like that. Oh, the same, like sine mx sine nx dx, and similarly cosine mx cosine nx dx. For that we had to use the product formula. So we're going to use product formula. Normally for an exam, what's gonna happen? You're gonna get the formulas, because it's like difficult to remember sometimes. So you're gonna get the formulas. So you can find the link in the description for that original video, which discuss like all the formulas and how to do a problem like that. Okay, so that's about trigonometric integrals. So next we're gonna go to trig subs.